Okay. Um, Good morning, everyone. My name is Jayant Thatte, and today I'm going to talk about cinematic virtual reality with head motion parallax. Um, I will start by I will start with a quick introduction of some of the terms in the title, and then as a way of motivation, I will talk about the importance of head motion parallax in cinematic VR. Then I will go over the four main contributions of my work. And after this, I will draw some conclusions. So let's actually start by breaking down the title. What is cinematic virtual reality? Based on the type of content that VR deals with, VR is classified into two broad groups, cinematic and synthetic. Synthetic VR primarily deals with computer-generated CGI content that must then be processed by graphics rendering engines before being rendered onto a head-mounted display. As opposed to this, cinematic VR deals with real-world environments that must be captured by a camera system and then processed and rendered onto a head-mounted display. And the key difference between them is that rendering in synthetic VR happens based on an underlying computer-generated 3D model, whereas in synthetic VR, rendering is significantly more challenging since we don't have access to this underlying scene model. In my talk, I will focus on the cinematic side of VR. Next, let's take a look at what head motion parallax means. Head motion parallax is the change in perspective due to viewpoint translation. And this could be either up or down or vertical motion, or it could be side to side or lateral head motion, or it could be back and forth, also called as looming motion. Currently, cinematic VR only supports head rotation, and any head translation of the viewer is ignored, and therefore there's no support for head motion parallax in cinematic VR. And the goal of my work is to be able to extend this support also for cinematic VR. Head motion parallax plays a vital role in making the VR experience realistic and comfortable and to avoid VR sickness. For example, head motion parallax has been shown to be critical for the feeling of presence or immersion in VR, and lack of head motion parallax degrades depth perception and can also cause visual fatigue and nausea. To further understand the importance of head motion parallax, we also conducted a subjective study where we showed viewers 6 different render settings. So there was monoscopic and stereo combined with 3 different parallax settings. The first one was no head motion parallax, which is the conventional way. The second one was only horizontal parallax, where the viewers were free to move within a horizontal plane, but any vertical head motion was discarded. And the third was full or unrestricted head motion parallax. The viewers were shown pairs of these stimuli or render settings, and within each pair, they had to rate these settings relative to each other on a 7-point scale from -3 to +3. We used 2 versions of a test scene, one with scene objects much closer to the viewer, and another one with scene objects much farther away. And we had 17 participants in this study. The key findings of this study are summarized in this graph on the left, where the y-axis shows the differential mean opinion score, positive is better, and the 6 different bars show the 6 different render settings. In each case, M corresponds to monoscopic and S is stereoscopic or 3D. And the 2 bars on the left are for no head motion parallax, the 2 in the middle are for only horizontal, and the 2 on the right represent full or unrestricted head motion parallax. The first thing that we notice is that the biggest boost in user preference comes from enabling head motion parallax. Second, in the absence of head motion parallax, simply switching from monoscopic to stereo or 3D rendering doesn't lead to a significant change in user preference. And finally, once we already have head motion parallax enabled, further adding stereo leads to an additional boost to the user experience. Additionally, we also measured the range of head motion for viewers that were seated in a chair. And we found that the horizontal range of motion was about 30 centimeters and the range of vertical head motion was ±9. So hopefully with this, I've convinced you that head motion parallax is something important and worth spending time into. Now let's take a look at a typical end-to-end cinematic VR system. On the one end, we have a system of cameras that will record real-world environments to be played back in VR. And on the other end, we have a head-mounted display where we will show views depending on the viewer's head position. Of course, rendering directly from raw camera data is really challenging due to the size of this data. And therefore, often raw camera data is processed and stored into a compact, easy to use intermediate representation. Rendering from the representation must be real time. However, the representation itself may be constructed offline. And this brings me to the 4 key contributions of this work. First, we explored 2 novel data representations for cinematic, for head motion parallax and cinematic VR. The first one we call stacked omnistereo, and the second one is called layered depth panoramas. Next, we build a 2-tier camera system that can record real-world environments to be played back in VR. And we propose a depth fusion algorithm that can robustly combine the information from all the rig cameras to synthesize wide baseline output panoramas. Next, we also demonstrate a real-time renderer that can take either of these 2 representations and synthesize real-time head motion parallax onto a head-mounted display. And finally, I will analyze the occurrence of disocclusion holes in the output as well as the output quality, and take a look at how the design choices in both the camera system and the data representation impact the output quality. And with that, let me move to the first main part of my talk, intermediate representations. Omnistereo is perhaps the most ubiquitously used VR representation today. It provides viewers with stereo in all viewing directions. However, it doesn't support any head motion parallax. Concentric mosaics were proposed as an extension to omnistereo and can provide viewers with horizontal head motion. However, they don't support any vertical parallax. And additionally, they require on the order of 40 panoramas to store a single frame. Next, we have cylindrical light fields that can result in convincing vertically as well as horizontally translated novel views. However, they don't support real-time rendering and also require on the order of 100 panoramas to store a single scene. Multiplane images combined with deep learning have been gaining popularity in the past couple of years. However, all of these approaches have been proposed for relatively high density capture and limited field of view applications. An extension to outward facing 360 VR-like applications remains an open challenge. In this work, I would like to start with the conventional omnistereo representation and then extend it to additionally support head motion parallax. To that end, let's take a quick look at what omnistereo is. Conceptually, we can think of omnistereo as being synthesized from a pair of rotating cameras on a turntable. The distance between these cameras, or the diameter of this circle, is usually said to be the same as the distance between human eyes, or about 6.5 centimeters. This is also called the baseline of the panoramas. In each direction, each camera captures a narrow vertical slit, and all of these slits are then mosaicked together to produce a left and a right panorama. In this work, we start with the conventional omnistereo, and then we add a depth component to each panorama. Next, we expand the diameter or the baseline of these panoramas. And the idea here is that so long as the novel viewpoint resulting from the viewer's head motion falls inside of this enlarged circle, we can synthesize high quality novel views by using depth-based view synthesis. The importance of having wide baseline panoramas is shown in these videos. Both of them show an end-to-end head motion parallax of 30 centimeters. The video on the left is synthesized using stereo panoramas with a conventional 6.5 centimeter baseline, and the one on the right is using wide baseline panoramas. In the video on the left, we can see significant flickering artifacts around this foreground tree due to in-painting and disocclusions, whereas the video on the right is synthesized correctly. Next, we would like to extend this representation to not only support horizontal parallax, but also support vertical head motion parallax. And this is done relatively naturally by simply stacking 2 of these on top of each other. And this gives us 4 panoramas, 2 in the top plane and 2 in the bottom plane, and the cylindrical viewing volume. Of course, in practice, we don't construct this representation from rotating cameras, but rather from this 2-tier camera system that I built. Here are a couple of examples of parallax synthesized from stacked omnistereo for a real scene. This is outside the Palace of Fine Arts in San Francisco. And here are a couple of more examples. In the toy example on the left, we can see that the colors of the metallic monkey head appear to change as the viewpoint shifts around. And this is because blending between the different stacked omnistereo panoramas allows us to generate some degree of view-dependent lighting changes. The video on the right shows perhaps the key limitation of stacked omnistereo in terms of these highlighted red pixels. These pixels are where none of the panoramas of stacked omnistereo had enough information saved to synthesize correct texture for these areas. These are called disocclusion holes, and in real applications, these will have to be in-painted using hole filling algorithms. So let's take a look at what causes disocclusions. Let's say we have this very simple scene with this blue background and an orange foreground. Let's say that the scene is captured by a single camera, as shown. Any portion of the blue background that is blocked from the camera's view by the orange foreground will not be captured in the source view. Now, if we try to visualize these scenes from a novel perspective, a portion of this blue background that was never seen by the camera must become visible to this eye. And this causes a disocclusion hole. Stacked omnistereo aims to address this by storing the scene from multiple different viewpoints with the hope that at least one of these panoramas would have saved the required background information to synthesize this novel view. However, as the scene geometry gets more complicated, even this is not guaranteed to eliminate disocclusion holes. For example, for this particular scene, the eye should have seen the blue object in the far background, but the camera on the left was blocked by the green object and the camera on the right was blocked by the orange object. And therefore, we will still get a disocclusion hole in this area. Our second representation aims to solve this problem by storing the occlusion information not from different viewpoints, but rather from a single reference point in a layered fashion. And the idea here is that we pick a single reference point, let's say somewhere over here, and then everything in the scene that's farthest away from this reference point will get saved in layer 1. So in this simple scene, it would just be this farthest blue object, and all of that gets saved as layer 1. And then everything that's directly in front of layer 1 gets saved in layer 2, and anything that's directly in front of layer 2 goes in layer 3, and so on. And this way we can essentially break the entire 3D scene into these layers, ordered by occlusion back to front. Note that each panorama is texture plus depth plus transparency. For a more realistic scene, it looks something like this. So this is layer 1, or the farthest, or the layer with all objects that are farthest away from the viewer. This is layer 2, which is everything in the front. And layer 3 has everything in front of layer 2, and then the frontmost layer 4. So again, altogether, it looks like layer 1, and then additionally layer 2, and then 3, and then the frontmost layer completes the scene. And the advantage of this is synthesizing correct views when the scene has a lot of occluders. So in this toy example, the scene geometry is very simple. There's a static background that's really far away, and there's this red and blue grid that's occluding the scene. As the viewpoint shifts around, in the video on the right that is synthesized by stacked omnistereo, we see significant flickering artifacts because of disocclusions and in-painting. Whereas the layered representation synthesizes the correct video as shown on the left. Next, let's take a look at what happens to the output quality as we change the number of layers in the representation. Of course, if we have a single layer, we have no ability to store any occlusion information, and therefore we get a lot of disocclusion holes shown here in black. But as soon as we add just a second layer, most of these holes go away, and adding a third layer makes the scene more or less complete. And this is in fact what we find in practice, that for most natural scenes, 2, 3, or 4 layers are sufficient to cover the entire 3D scene. Here are a couple of examples for real scenes for parallax synthesized using the layered depth representation. The video on the left is from Stanford Memorial Church, and the one on the right is outside my department. Of course, both of these representations come with their own limitations. Stacked omnistereo struggles to synthesize correct texture when the scene has rapid occluders, like the striped back of this chair. Both of these representations do not currently support surfaces that are partially transparent or partially reflective. And of course, since both of these representations depend on depth, for a real scene, if the depth estimation goes wrong, we get either distortion or ghosting artifacts, as shown with this red circle. To summarize, we have seen that head motion parallax is critical for the overall quality of experience in VR. Representations storing the scene with just a few panoramas can effectively synthesize head motion parallax. Layered depth panoramas yield better performance when the scene has a lot of occluders, and stacked omnistereo can produce some degree of view-dependent lighting by blending between these different panoramas. Now that we have looked at these two representations, let's discuss how they can be constructed for real scenes using a system of cameras. Most of the VR camera rigs available today consist of a single ring of cameras all in one plane. And while these can capture enough novel perspectives to synthesize horizontal head motion parallax, they don't capture any vertically shifted perspectives. More recently, Facebook came up with spherical cameras that can provide horizontal as well as vertical head motion within a spherical volume. However, through our subjective tests, we found that the range of horizontal motion is typically much larger than the range of vertical motion. And therefore, the head volume that we would like is not so much a sphere, but rather a flat cylinder. We can easily get a cylindrical head volume by simply stacking two of these cameras on top of each other. And that's in fact exactly what we do. Here's a picture of the camera system that I built. Each camera, so the cameras at the top and the bottom are first generation Facebook Surround 360 cameras that have been partially deconstructed. The field of view of each lens is 77 degrees. The radius is 21.8 centimeters. The vertical separation is adjustable with a max separation of 30 centimeters. We have 14 cameras in each ring, and each region of the scene is observed by around 6 cameras, 3 in the top ring and 3 in the bottom ring. And finally, we get 45 minutes of recording with a portable power supply. Next, I took this camera around campus and recorded a bunch of real scenes to be played back in VR. Now that we have looked at this camera system, let's discuss conventionally how panoramas are typically generated from a ring of cameras. So here I'm showing a single ring of cameras with just 2 cameras in this ring. We would typically define a viewing circle, and from each point on this viewing circle, we shoot out tangential light rays and copy over the image information from these corresponding cameras. However, for points in between, we don't have a physical camera at these locations. And therefore, a virtual camera must be synthesized by interpolating between the 2 adjacent physical cameras. However, since this method uses only 2 cameras at a time, it is highly sensitive to errors in individual depth estimation. Moreover, this method breaks down at about 9 or 10 centimeters baseline and cannot synthesize wide baseline panoramas due to field of view limitations. And finally, it doesn't take advantage of the 6-fold overlap that we have in our camera rig. Instead, we would like to come up with an algorithm that can jointly use the information from all of the rig cameras to synthesize robust wide baseline output panoramas. To that end, we start with raw camera capture and then perform black level correction and color correction to get RGB images for each camera. Next, we use an off-the-shelf depth estimation algorithm to get one depth map for each image. At this point, we have one color image and one depth map for each camera in our system. Some of the depth maps for a real scene are shown on the left over here, and we can see that the individual depth maps are quite noisy and prone to errors. Our depth fusion algorithm aims to combine all of these to synthesize an output panorama that has relatively few errors compared to any of the inputs. A zoomed crop of the output is shown for comparison, and we can see that it indeed has fewer errors than any of the individual depth maps. So let's take a look at how this works. Here I've shown just 6 source depth maps. We define an output view, and for each pixel in the output view, we choose a certain assumed depth. And using this assumed depth, we warp this point onto all of the source views. Then we read the depth from the source depth maps at these locations. And using these red depths, we project these points back onto the output. And this gives us a cluster of reprojected points. Next, we sweep across assumed depth and take a look at what happens to these reprojected points as the depth value changes. And the idea here is that when the assumed depth matches with the true physical depth at that point, all of these reprojected points will agree with each other. And this is in fact what we find. So the 3D volume on the left, along the horizontal XY plane, it shows the pixel coordinates of the reprojected points. The vertical axis shows the different depth slices for the assumed depth. And the different lines correspond to different sources. So each line corresponds to the reprojected points from one particular source image. The video on the right simply shows 2D slices of this 3D volume played as an animation. And what we find is that all of these reprojected points come together at one particular depth and then they diverge again. And this is indeed the true depth for this pixel. And simply repeating this across all pixels in the output view, we can generate an output depth map. To understand the robustness of this method to noise, we artificially corrupted our ideal depth maps with 3 different types of noise. So we have black and white blob noise, as shown over here. Plus we have 3% random offset in disparity space and 3% white noise. And we can see that despite having noisy inputs, the fused output looks relatively usable. Moreover, we can get not only the depth of the most foreground object, but we can also retrieve the depths of any occluded objects behind the foreground, so long as at least a few cameras saw this background portion. This is shown in the output depth map on the left, and the pixel of interest is highlighted in red. That's over here. The 3D volume on the right again shows reprojected pixel coordinates as we sweep depth. We can see that we get 2 distinct intersections for 2 different depth values. The first of which corresponds to the depth of the glass on the table, and the second one actually corresponds to the depth of the table at this pixel directly behind the glass. And of course, we don't have to be limited to just the reprojected pixel coordinates. We can also incorporate the RGB information from the source views and define a scoring function to decide how well these points agree with each other. The scoring function is shown on the right. And again, we can see that we get 2 distinct peaks, one for each depth value. Example panoramas for a real scene are shown on this slide. The image at the bottom corresponds to a depth map, and the image on the top is the corresponding texture component. And here's an example for a different scene. Once we have the depth map below, the texture component above is synthesized by simply doing a texture lookup in the source RGB images. To summarize, we have seen that vertically stacked camera rigs can capture both horizontal and vertical parallax. Much wider baseline panoramas can be synthesized by jointly using all the available rig cameras rather than just using a pair of cameras at a time. And depth fusion using reprojection error can combine erroneous individual depth maps to produce a robust output that has fewer errors than any of the inputs. So far, we have looked at 2 different data representations and how they can be constructed for real scenes. Next, let's take a look at, once we have these representations, what is the way to synthesize real-time head motion parallax from these representations. For that, let's take a look at a single texture plus depth panorama. And this could be coming either from the stacked omnistereo representation or the layered depth panorama representation. This first step is common for both of them. We start with just the depth component, and knowing the target pose, field of view, and resolution, we can warp this depth onto the target viewport. Then we run a depth interpolation stage, at which point we get a smooth interpolated depth map for the output. Then for each pixel in this output depth map, we run these calculations backwards and figure out where this point came from in the original texture panorama. And then we perform a bicubic texture lookup, and this gives us a hypothesis for what the novel view could look like. For stacked omnistereo, we have 4 such texture plus depth panoramas, and this means we get 1 such hypothesis from each panorama. By design, all of these hypotheses will agree with each other everywhere except where we have disocclusion holes shown in black, or where the scene is non-Labortian. Then there's a final blending step, which gives us the final output view, usually without a lot of inpainting. For the layered depth representation, these different panoramas actually represent different layers, and therefore they have to be combined using alpha compositing. To get the output color, we simply start with the color and transparency of the frontmost layer, and then work our way backwards using standard alpha compositing. A video showing the real-time renderer this video shows the results of the real-time renderer for a real scene using stacked omnistereo. We can see the parallax between the bushes in the front and the fountain and the water in the far background. Here is another example. The black regions actually show the disocclusion holes, and they appear when the viewer goes outside of the cylindrical viewing volume. And here's a final example for stacked omnistereo. We can see the parallax between the tree in the foreground and the trees in the far back, and also between the picnic chair in the front and the bushes behind it. And now here's an example of synthesized parallax using the layered depth representation. And we can also switch off the different the different layers to take a look at how the scene is constructed. So this now shows just the layer 1, or just the backgroundmost layer, and we can see that we get a lot of disocclusion holes until we enable the remaining layers back, and then the scene becomes complete. And here is an example inside Stanford Memorial Church. You can see the vertical parallax over here. And in practice, actually, I found that the effect is quite pronounced. When I've shown this demo to people in person, most people tend to get sick within about half a minute without head motion parallax. And then when head motion parallax is enabled, the experience becomes a lot more comfortable and a lot more natural. Here we can see the parallax between the people in the front and the people in the far background. And here is a final example. With layered depth panorama representation, we can see that the striped back of the chair is actually synthesized correctly. This is not possible using the stacked omnistereo representation. Now some specifications. The input to the representation are 4 panoramas coming from either of the 2 representations with a resolution of 4K by 2K. The output is stereo at full resolution, that is 1344 by 1600 pixels per eye on Oculus Rift. It takes about 13.5 milliseconds per frame, which comes to about 75 frames per second. The laptop, the demo is running on a laptop with an 8 GB NVIDIA RTX 2080 GPU. And the demo was built using CUDA and OpenGL. To summarize, we have seen that both stacked omnistereo and layered depth panoramas can synthesize real-time head motion parallax, and a single GPU can render full resolution stereo views at VR frame rates. And now that we have looked at the three main components of a VR pipeline, I will move on to the final part of my talk, analysis. Disocclusion holes are one of the key reasons for degradation in the output quality when using depth-based novel view synthesis. Here I'm showing a histogram of the PSNR of all in-painted pixels across thousands of novel views. And we can see that in-painted pixels consistently have a low PSNR. Moreover, in-painting is challenging in real-time applications and often leads to jarring and unconvincing results. So we would like to design camera systems and representations so as to minimize disocclusion holes within the viewing volume. Understanding the high-level behavior of disocclusion trends within the viewing volume typically requires synthesizing hundreds of novel views and then measuring disocclusion holes in each synthesized view. This is often time-consuming and computationally intensive, and instead we would like to come up with a theoretical model that can efficiently predict the disocclusion behavior using just the source depth map. To that end, we break down general 3D motion based on the viewing direction into a lateral component, a looming component, and a vertical component. And then under random viewing direction and random scene geometry, we can define a disocclusion hole indicator variable A, where A equal to 1 indicates a disocclusion hole and A equal to 0 indicates that the information is available from the source view. We can model A as a Bernoulli variable with parameter P, where P depends on the viewpoint translation, where the three components are X, Y, and Z. To understand the behavior of this function, we used Middlebury stereo dataset and synthesized translated novel views with each of the three types of translation. The y-axis here shows the percentage of the output view that was missing due to disocclusion holes. The x-axis shows the magnitude of translation, and the three different colors show the three different types of motion. In each case, the circle represents the measured data, and the straight line shows a linear fit. And we can see that the disocclusion behavior is actually piecewise linear along each axis. And this allows us to model the function f as a piecewise linear function ax plus by plus cz, where a, b, and c are constants along each half axis. Notice that there's no bias term, and this is because when the translation is 0, by definition, we cannot have any disocclusion holes. The slopes a plus through c minus are model parameters that depend implicitly on the scene geometry, and these are estimated using the source depth map. Next, we tested this model on the Middlebury stereo dataset, where the input and output are both single viewport, and the output is translated with some translation magnitude and translation type. In each graph, the y-axis shows the percentage of the output view that's missing due to disocclusion holes, and the x-axis shows the viewpoint translation in centimeters. The graph on the left shows vertical translation, and the one on the right shows lateral head motion. The blue line shows the model prediction, and the red line shows the measured data. Additionally, we also measured the Pearson correlation between the model and the data for each of the three types of motion, and these numbers are shown at the bottom of the slide. In general, we found that the model agrees with the measured data reasonably well. Looking at this graph on the left, we can already draw our first conclusion that moving up on an average leads to more disocclusion holes than moving down. And this is because for most natural scenes, there's a ground plane with objects placed on the ground plane. And when the viewer moves up, the viewer gains the ability to look past these foreground objects into a portion of the background that might not have been captured. And this causes more holes when moving up than moving down. And this means that both data representations as well as camera rigs should be placed higher up in the scene so that more viewer motion is downwards rather than upwards, thereby minimizing disocclusion holes. Next, we would like to use this model for the case when we are synthesizing novel views using stereo panoramas. Let A be the indicator variable when we use both the left and the right panorama together, and A1 and A2 be the indicators when we use either only the left or only the right panorama. We know that we get a disocclusion hole in the final output only if we have a disocclusion hole in each of the two hypotheses. And this means that A is A1 intersection A2. And this allows us to write the expectation of A in terms of A1, A2, and the correlation between them. Next, we measure this correlation curve for panoramas with different baseline and for different scenes. And that curve is shown on the left, where the x-axis shows the normalized viewpoint translation, and the y-axis shows the correlation between A1 and A2. We found that this curve is actually independent of the panorama baseline or the scene geometry. And therefore, we were able to use this curve in our model to estimate the disocclusion behavior. The model prediction is shown in the middle, and the observed data is shown on the right. The x-axis in each case shows lateral head motion in centimeters, and the y-axis shows disocclusion holes in percentage. The different lines show panoramas with different baselines, where the blue line in the middle corresponds to monoscopic panorama, and the outermost green line shows a panorama with a 60 centimeter radius. Looking at this graph on the right, we can draw a few more conclusions. The first is that within the viewing circle for each stereo panorama pair, the disocclusion holes are low. For example, this red line corresponds to a panorama with baseline 30 centimeters. And we can see that so long as the viewpoint falls within plus minus 15, the disocclusion holes are relatively low. Also, outside of this region, disocclusions tend to increase linearly. And this means that stacked omnistereo panoramas must be wide enough to encompass the entire range of anticipated head motion to minimize disocclusion holes. Next, we take a look at the effect of having a two-level camera rig versus having a single ring of cameras placed either at the top or at the bottom of the viewing volume. In this case, the y-axis shows the disocclusion holes in the output view when we use all the available rig cameras jointly. The x-axis shows the vertical head motion in centimeters, and the two vertical dashed lines show the limits of the cylindrical viewing volume. The black line corresponds to a two-level camera rig, and the red and the blue lines correspond to a single ring of cameras placed either at the bottom or at the top of the viewing volume. First, we can observe that to minimize disocclusion holes within this volume, we really need a two-level or a non-planar camera geometry. Second, if we have a single ring of cameras, placing it higher up within the viewing volume causes fewer disocclusions than placing it lower. And we can see this because the blue line is much lower than the red line within these two dashed lines. Next, we take a look at the effect of having different numbers of panoramas in the number of disocclusions in the output view. So far, we have looked at stacked omnistereo as consisting of 4 panoramas, 2 in the top plane and 2 in the bottom plane. However, the framework itself can handle fewer or more panoramas with different radii and different heights. So we could, for example, have a single panorama at the center, or we could have a stereo pair of panoramas in a single plane, or we could have a stereo pair in one plane and a single monoscopic panorama in a lower plane, or we could have 5 or 6 panoramas and so on. The video on the right shows what happens to disocclusion holes as we increase the number of panoramas in the representation. The x-axis shows the number of panoramas. The y-axis shows the percentage of the output that's missing due to disocclusions. The red line corresponds to the layered depth representation, and the blue line corresponds to stacked omnistereo. We can see that the layered depth representation minimizes disocclusion holes using fewer panoramas compared to stacked omnistereo. Moreover, unlike stacked omnistereo, it is possible to inpaint directly into the layered representation, thereby reducing or even eliminating disocclusion holes during render time. Next, let's take a look at what happens to the output image quality as we change the number of panoramas. The graph on the left shows the output PSNR, and the graph on the right shows the output SSIM. The x-axis again shows the number of panoramas in the representation, and the red line shows layered depth panoramas, and the blue line shows stacked omnistereo. We can see that layered depth panoramas lead to a slightly higher image quality using fewer panoramas compared to stacked omnistereo. And this is again because the generated output views have fewer disocclusion holes. To summarize, we have seen that moving up causes more disocclusion holes than moving down, and therefore camera rigs and representations should be placed higher up within the viewing volume. Stacked omnistereo panoramas must be wide enough, and the vertical separation must be large enough to contain the entire range of anticipated head motion. A non-planar camera geometry is essential to support vertical head motion parallax. And layered depth panoramas produce fewer disocclusion holes and a slightly higher PSNR compared to stacked omnistereo using fewer panoramas. And with that, I will conclude. So far, we have seen that head motion parallax is critical to the overall quality of experience in VR. Layered depth panoramas produce fewer artifacts when the scene has a lot of occluders. And stacked omnistereo can synthesize some view-dependent lighting changes by blending between the different panoramas. A two-tier or non-planar camera geometry should be used to enable vertical head motion parallax. Reprojection error can robustly combine erroneous individual depth maps to generate an output that has fewer errors than any of the inputs. And wide baseline panoramas can be synthesized when we use all the available rig cameras jointly, compared to using just pairs of cameras at a time. We saw that both of these representations can render real-time head motion parallax on a single GPU. We also saw that stacked omnistereo panoramas must be wide enough and the diameter and tall enough to encompass the entire range of head motion to minimize disocclusion holes. And layered depth panoramas produce fewer disocclusion holes and lead to a slightly higher image quality compared to stacked omnistereo using fewer representation panoramas. And with that, I would like to thank my committee for their time and for being here today. Professor Pauly, I never really got to interact with you much, but anytime I sent you an email with anything related to my defense, you were always super prompt and very helpful. And I appreciate that. Thank you so much. Tony, I have enjoyed working with you and some of the members of your group. And thank you for all the discussions regarding size and depth perception. I found them quite enriching. Brian, it has been such a wonderful and positive experience getting to know and working with you and Trisha and Joyce. And I've also benefited a lot by discussing my research with you at various points through my PhD, particularly also when I was conducting my subjective tests and analyzing the results of those tests. And also outside of work, I've always enjoyed informally chatting with you, either after our Cyan meetings or otherwise. So thanks for always being available anytime I wanted to discuss anything. Gordon, from you, I've learned to take a step back and focus on the big picture when, like a lot of my PhD friends, I tend to get stuck in research rabbit holes. You've always been good at reminding actually all of us to take a step back and think about what is the exact problem that we are trying to address and whether that is the right problem to address and so on. And asking these kind of high level questions is a habit that will, I think, stay with me past my PhD. Also, thank you for all the skiing trips you have organized. I remember the first one that I went to, I was face planting every several feet. Yeah, and you have helped me improve as a researcher and also as a skier. So thank you so much. And finally, Professor Giraud, I couldn't have asked for a better PhD advisor. Thank you so much for supporting me through everything, through all of my struggles, usually professional, sometimes personal. And I have learned so much from you that it's difficult to list it out all in words. So I will just say you have really helped me evolve academically compared to the student that I was half a decade ago. So thank you so much for everything. I would also like to thank the wonderful colleagues with whom I've had the privilege of collaborating. No research work is done by one person, and I had the privilege of working with JB, Hari, Trisha, and Tamay at different points in my PhD. And all of you made work feel a lot less like work and more like a fun, adventurous journey together. So thank you for that. I would also like to specially thank Brian and his entire team at Facebook for donating the Surround 360 cameras for my work. And also for always being patient with all the questions and technical difficulties that I had while using the cameras. The cameras have played a truly vital role in advancing my work. So thank you so much. And then a big shout out to all members of the IVMS community. It has been such an inspiration working alongside all of you for the past 5-6 years. And going forward, I hope that I get the chance to work with at least some of you at some point again. I would also like to thank everyone from Gordon's group for the numerous informal research discussions over coffee. They were always really stimulating and at times played a key role in keeping me motivated with my work. Also a special shout out to Robert, who is the most wonderful ski instructor that I've ever met. So yeah, thank you for that. Through my years at Stanford, I've had the privilege of meeting some of the most wonderful and genuine people and the good fortune of calling them my friends. And thanks to all of you, the past half a decade has just flown by. It has been so memorable and fun and adventurous. And it really wouldn't have been the same without all of you. So thank you so much to all of you guys. I would also like to mention my grandparents, who have always played a big role in my life. Having long, meandering technological discussions with my grandfather is something that I have always enjoyed. And painting together with my grandmom sitting side by side is perhaps my favorite thing in the world. And last and perhaps the most important, I would like to thank my parents. Not even a fraction of any of this would have been possible without their unwavering, continuous support and guidance through all these years, through my entire life. And they're actually also watching this live from India right now. So thank you so much, Mom and Dad. Yeah, and with that, thanks to all of you here in the audience for giving me an hour of your time to share some of my work. With that, I will conclude. Thank you so much.